Good morning, physics class. Today I want to do some notes on one of our last topics today, that is nuclear physics. You see the teaks up in front of you here. You have to know examples of atomic, nuclear, and quantum phenomenon. The one you don't see here, A, has to do with calculating energy released in nuclear reactions. So that's what this video is going to focus on. So there's different types of nuclear reactions. Nuclear fusion is what happens in the sun, where there's high temperature, high gravity, and high pressure. So you have atoms with low atomic mass being fused together by the high heat and gravity of the sun to produce heavier elements. So in this image, you have 4 atoms of hydrogen, and they're being smushed together to create helium. Now, each of these, if you remember from 8th grade science, has an atomic mass of 1. Helium has an atomic mass of 4. That's because each of these is basically 1 proton and 1 electron. All right, so when these all get fused together, you end up with 2 protons and 2 neutrons, 2 electrons, and orbiting this nucleus, and 2 electrons left over, plus energy being created, and we can actually calculate that energy, and we will. Other sorts of nuclear reactions you have are nuclear fission or fission. This happens both in nuclear reactors and nuclear weapons, where heavier elements like plutonium and uranium are split apart in controlled ways, making elements with smaller atomic masses releasing energy. This here is what it looks like when some nuclear reactors start up. So you get this really cool blue glow in the nuclear reactor. Those things that you're seeing down there are control rods, which absorb some of the neutrons that are flying around to prevent it from becoming a nuclear explosion, and instead just creating nuclear energy. The cool thing about nuclear reactors is that they actually are a thermodynamic engine at the end of the day, because they're heating water, creating steam to drive turbines to create electricity. So nuclear energy is converted to thermodynamic energy, which is converted to mechanical energy, which is converted to mechanical energy, which is converted to electrical energy, and an electrical generator. That's something we do need to talk about. In a nuclear weapon, a chain reaction of released neutrons reaches critical mass, creating a nuclear explosion. So one free neutron comes in here, splits this uranium into barium and krypton, and it releases some extra neutrons, which splits more atoms of uranium, and these things keep splitting up into lighter and lighter elements, elements with smaller and smaller atomic masses. All right, so let's talk about the calculations you've actually got to do. Okay. In order to calculate energy released in a nuclear reaction, you need to use Einstein's famous formula, E equals mc squared. Okay, E is energy, m is mass, c is the speed of light, and we're just going to square it. Okay, this is an example of a question you might see. You get that same diagram before, and you'll be told you've got 4.031 kilograms of hydrogen forming 4.003 kilograms of helium and 0.001 kilograms of positrons, positively charged electrons. Isn't that neat? What's the magnitude of the energy released? And you have a number of answers in joules. So let's figure out how to do this. First, you need to figure out what's the reactant, what's the product. The reactant is just like in a chemical equation, what we're starting with. In this case, 4.031 kilograms of hydrogen. And we're ending up with the product, 4.003 kilograms of helium, 0.001 kilograms of positrons, and some X amount of energy, right? Now take your time with this, pause when you need to. We've got our mass of the reactants, our mass of the products. These things have to be equal. So we're starting with 4.031 on this side, 4.003 plus 0.001 plus x. Okay, you add these two up, they don't have a variable. As we move down, 4.031 has got to be equal to 4.004 plus x. Let's then subtract 4.001 from both sides. And we get that x is equal to 0.027. That's actually kilograms. What this is telling us is that 0.027 kilograms of mass disappeared. It's missing. There should be more mass here for the law of conservation of mass and energy to be obeyed, but it's gone. This is called the mass defect. So, since matter can neither be created nor destroyed, Einstein's formula, E equals mc squared, lets us calculate how much energy that mass was converted to. So now that we have that mass defect, how much mass is missing from this reaction, we can calculate how much matter was converted into pure energy. That's the E part. Okay. I'm going to try and make sure I'm not running over on the time I can use here. All right, good on time. Let's finish this up. Okay, energy is measured in joules, mass in kilograms. The speed of light has a given value, which is 3 times 10 to the 8th meters per second. Not too hard to work with there. So E is our variable because we know the mass that had been converted and we know the speed of light. So we're looking for the energy released that had to come from that 0.027 kilograms of missing mass. So our formula ends up looking like this once we plug everything in. E equals 0.027, our missing mass, times the speed of light, 3 times 10 to the 8th, squared. Now, don't forget this part. Our rules for math with scientific notation. When you're multiplying scientific notation, multiply the coefficients and add the exponents. So for example, in this one down here, 4 times 10 to the 4th times 2 times 10 squared is going to be 4 times 2, that's 8. That's multiplying the coefficients and adding the exponents. 4 plus 2 equals 6. Not hard. And we're not going to need to deal with dividing right now, so I'm not going to even bother with it, but you see it there. Okay, so let's understand what c squared is. C squared is really c times c. So the speed of light times the speed of light. If the speed of light is 3 times 10 to the 8th, then we're just going to multiply these two. Multiply the coefficients. 3 times 3 is 9. That's what you see there. Okay, add the exponents. 8 plus 8 is 16. So c squared is really 9 times 10 to the 16th. It'll always be 9 times 10 to the 16th because it's always going to be c squared. That's the formula. This turns out not being very hard. So this formula is really the mass we're losing times c, because that's what c squared is. Right? And then, what is it really? 0.027 times 9 times 10 to the 16th. Okay. So, to finish this, it's pretty simple. All we've got to do is multiply this, because this doesn't have any exponent, any scientific notation to it. We'll just multiply it times 9. So, 0.027 times 9, and we'll keep the 10 to the 16th, giving us E equals 0.243 times 10 to the 16th. Okay, now unfortunately, that is not proper scientific notation, because for it to be proper scientific notation, our coefficient must be between 1 and 10. 1 or greater and less than 10. This is less than 1, so we've got to fix it. Okay, so as we did before when we were doing calculations with gravity, we're going to split this up. So 0.243 times 10 to the 16th. Another way of saying that is 0.243 times 10 to the 16th. You know that, right? Then convert this number here, what was our coefficient, into scientific notation. Okay, so we've got to move the decimal over one spot. So 0.243 becomes 2.43 times 10 to the negative 1. Okay, so we moved it to the negative power because this is a number less than 1. If it was 24.3, it'd be 10 to the positive 1. And you can always check this math too. Okay, so this coefficient is really 2.43 times 10 to the negative 1. So let's do that. 2.43 times 10 to the negative 1. That was the coefficient. And then this was our 10 to the 16th. We're just going to put a 1 in there to make it easier to comprehend for our rules of math with scientific notation. So 2.43 times 10 to the negative 1 times 1 times 10 to the 16th. Now let's just use our rules for math with scientific notation. So 2.43 times 1, because we multiply the coefficients, is 2.43. We add the exponents, negative 1 plus 16 is 15, and we're done. 2.43 times 10 to the 15th joules. 2.43 times 10 to the 15th joules, and there's your right answer. So now you're going to get some practice doing this yourself. Let me know what you need, and good luck.